Hi, I am Uri Vered, author of the book Intersystem EMC Analysis, Interference and Solutions, published by Artec House. Today I would like to address one of the issues covered in the book, the probability of the frequency difference between two devices. Reason we are interested in being able to calculate this probability is as follows. We consider the case where one device interferes with another if both use the same frequency. A certain frequency difference, df, is required to avoid interference. The frequency one device uses is a random variable with a certain probability distribution. The frequency the other device uses is also a random variable with another probability distribution. The frequency difference between these non-correlated devices is a random variable as well. We are looking for the interference probability. The interference probability is the probability that the frequency difference between the devices will be below the minimum required frequency separation, df. First, we must calculate the probability density function, the PDF, of the difference between the two random variables. Then we need to calculate the cumulative density function, CDF, which is the integral of the PDF. The PDF of the difference between two random variables is the convolution between the two PDFs. When both random variables have a uniform distribution, we can easily calculate the convolution. However, I would like to deal with a more complicated case where one or both devices do not have a uniform frequency distribution function. A typical example is the Link 16 radio. The radio hops between 51 non-contiguous frequencies from 969 to 1206 MHz in 3 subbands. These are the frequencies used by Link 16. There are 14 channels in the lower subband, 5 channels in the mid subband, and 32 channels in the higher subband. In between, there are 2 non-equal guard bands to protect the two devices from interference with each other between the IFF 1030 and IFF 1090 MHz. To calculate the CDF of this case, I will use a procedure which I name the counting procedure. To demonstrate the calculating procedure, we will use a simple example where both devices use discrete, non-uniform and not necessarily equal frequencies. One device uses 5 frequencies and the other 7. Now we build a matrix with all device A frequencies at the top row and all device B frequencies at the left column. Now we calculate for each square in the matrix the absolute difference of frequency between the frequency of device A and device B. We call this difference I. For example, between 35 MHz of device A and 32 MHz of device B, I equals 3 MHz. Between 43 MHz of device A and 33 MHz of device B, I equals 10, and so on. In the next step, we count for each frequency difference I in how many squares does I appear in the matrix. We name this number Ni. This table is the counting result, Ni as function of I. For example, for I equals 0, there are 2 cases. For I equals 1 MHz, there are 3 cases. For I equals 17, there are 2 cases. In the next step, we find the total number of squares in the matrix, which we name n. It obviously equals the product of the number of frequency of device A and B. In our example, n equals 5 times 7, or 35. Now we find the PDF, the probability that I equals df, which equals the ratio between Ni and n. And in the final step, we find the CDF, the probability that I is less or equal df, which is the sum of all Ni over n. Or yet in another form, equals 1 over n, the sum of all Ni's from I equals 0 to df. And here we see the final result in a graphical way. The CDF, the probability of the frequency to be less than a certain value. For example, the probability that the frequency difference will be less than 10 MHz is 70%. In another example, we apply this counter procedure to find the probability of the frequency difference between the link 16 and the two IF frequencies 1030 and 1090 MHz. For example, link 16 and IFF equipment are mounted on an aircraft. Normally, the antennas are mounted far enough from each other so that interference cannot occur due to the guard bands between these devices. But let us examine a case where the antennas are too close and therefore interference may appear. We have calculated the frequency difference to avoid interference and found, as an example, that the minimum DF is 40 MHz. Here we see the final result of the CDF, the probability of the frequency difference between link 16 and the IFF. The probability of the interference, where the requirement is 40 MHz difference, is 22%. The counting procedure can be used for devices using uniform frequency distribution as well, as detailed in the Intersystem Analysis book.